I was going to post it on Thursday, I believe, and then with the fires and all that on Friday. You guys know I had to rush home after school, just because I was trying to beat the freeways closing down and pack a bag for my dog if my roommate needed to take him and just kind of get out of there. And then I came actually back down the valley so that if the freeways closed, because I didn't think the school would close because it didn't affect the school in any way, shape, or form. But that's okay. I mean, all of LAUSD closed down, so it makes sense that our school closed down too. Like, they were just trying to be wise. But anyway, we can be praying for all the schools that are over, like Pacific Palisades and Viewpoint, and there are lots that are in the direction of the fire right now that are closed down today. But anyways, so I didn't post a related rates video for you guys over the weekend. I kind of just let you have the weekend because you guys really didn't have any calculus homework besides test corrections, right? You had HOCO and that sort of stuff. But to be honest, related rates, you really want to check out tutoring videos. And so I'm probably going to, with this homework that's not due until Thursday, I did find one good video that I liked. And so if I have time, I sadly have like a parent-teacher conference thing today at 3:30, so I won't be available at 3:30 on. If you need me, come quick after school, but then I'm popping actually out of my room. It's the only way I can really ever meet with parents and students because you guys know my room gets crazy. So I'm leaving at 3:30 today just to go for a conference, and so I won't be available. But I'm going to try to get that video online. There's a lot of them, though. Khan Academy, Patrick JMT, the organic chemistry tutor, whatever that guy's name is. There's the girl, I need to remember her handle, poor thing, because all I have is she's the one with the lazy eye, but she explains calculus really well. Like it's a sleepy eye, it's not, I don't know, but she explains math really well, she's really cute. But anyway, I think she's like a college tutor. She does a good job on it. But related rates, guys, if homework isn't making sense, which it very possibly might not, because it's not, look at forever number 17, I know, I need to update 18 and 19. Those are basic in the sense of there's a rule, you memorize it. Yes, functions get complicated, but when taking derivatives, you have a set number of rules, no big deal. There's a rule, you should have it memorized and then use it. Yes, U prime gets weird. Yes, well, you guys are doing test corrections on how derivatives get weird, right? But for related rates, they're word problems. And so I'm going to try to give you as many video options, resources as I can, like in a post. I probably won't make it like actually required, but maybe I'll have you commenting which one you liked better or which one was most helpful to you. I might have that be like the credit for the assignment, just like a comment in the actual resource thing that I give anyway. But that's going to be coming because it's not, if it's a tricky topic to you, you should listen to someone else explain it besides me. Does that make sense? Cool. So to that end, let's go ahead and get into, I think I updated all of Google Classroom and I updated your calendar as well to every time that we miss a day of school, everything gets thrown off. And it's okay, like we did what we thought we needed to do. But I think everything has been updated. Go check out your calendar for the next test date and all that stuff. I believe it's next Tuesday. Now, my juniors, why is that rough? Okay, because you have the retreat this Friday, right? Am I crazy? Okay. Heads up, test was supposed to be, I think, this Thursday at some point before all the fire days. So we can't have it Friday because juniors are leaving, and I don't want to have it Friday. Friday is going to be basically a work day for seniors. And then juniors, you don't miss anything besides a work day. Oh, are you guys here on Friday?
We leave, I think,
at lunch. Oh, so you're here for period 1. Period 6 is going to miss out. So my juniors, you get a work day on Friday, which is nice with the test review. But then you have your retreat all weekend. Why isn't the test Monday? Because it's just an awful idea and you're coming back from your retreat. But then I need to have the test on Tuesday. Does that make sense? Okay. So anyway, check out your calendar if you guys want to check out any other details. But yes, Kyle, our homework is due on Thursday, and this is the final section of Chapter 2B. You guys heard that, right? Yeah. This is the final section of Chapter 2B. Here we go. I was showing just a second ago something that Kyle saw. I'm not sure if the rest of you guys saw, but before we get to this little demonstration of related rates, let's talk about the tools we need to solve related rates. Related rates, it's a basic category of word problem. At least that's what the name's going to hopefully draw your attention to. Where there are two real things you need to remember. Just one. I'm going to fill them in right now. It's not a big deal. So chain rule. We know chain rule, right? What does chain rule refer to? Derivatives of?
complex.
Not complex, but you're close. composition of functions, f of g, f of u, right? And we can remember u prime, so then whenever we're doing chain rule, remember whenever we're taking a derivative, and I'm going to put it d dt, which is kind of weird, of some sort of f of u, we'll do it like that. We're going to have f prime of u times u prime. Now, why did I put a dt? What is usually here?
Yeah, dx.
Usually a dx. Let me show you something kind of weird, okay? What if I was to, well, let's see, what shape do we have down here at the bottom? Don't we have a conical tank? You might not see the entire thing, but do you guys see the cone?
Yes.
Okay. If you guys read this problem, we are going to in just a second, I believe this cone is being filled with water. It is being filled with water. What's changing? Well, first of all, what are the different dimensions of a cone? Like, what are the different quantities involved in it? Not length. Height. The height of the water. Not width. The radius, because it's circular.
Yeah.
So if you want to think width, it's circular. It's going to be radius. And that's always changing, right? The surface area or the surface of the water isn't always getting bigger, or if it's draining, always getting smaller. So the radius is changing. The height of the water in the tank is changing. But what else is changing? And what dimension or what quantity? Volume. So volume is changing, radius is changing, and height is changing. Wait a minute. Isn't there like a volume formula that relates all of those variables?
Probably.
Oh my goodness. Hold on. Cone, volume.
Yes.
There's a formula, right? Now, you might not have it memorized, but in the covers of our books, don't we have tons of geometry formulas?
Yes.
And doesn't Siri know math? And she can Google math too and be like, hey, what's the volume of a cone, Siri? If she can add and subtract and multiply and raise their powers, I think she can even take derivatives really basically. I think she can look up, she has this Wolfram Alpha mathematical computing brain. But anyway, coming back. We can find this geometry formula, right? And the geometry formula is 1/3 pi r squared h. Because pi r squared h would be a cylinder, area of the base times the height, but a cone is changing. Maybe you remember, that's why it has to have this extra constant. But long story short, none of those are t's.
No.
But what's happening as time passes? All of those quantities change.
Whoa.
So my independent variable isn't height, radius, or volume. Not that it could never be. Not that it could never be in a different type of word problem where this wasn't built on time, and as we zoom in, maybe you'll see it's built on time. Maybe volume would be changing with respect to r, with respect to h, maybe. But in this case, they're saying time is passing. If you were to look at the rates, you would have per second, or per minute, or per hour. It's with respect to time. Now, v is not time, r is not time, h is not time, so why do I have this written down underneath implicit differentiation? Implicit differentiation says take the derivative as it is. Is this volume formula in terms of time? Just like we had some formulas where f was not in terms of x, and we just said go for it. This v is not in terms of t, and we're just going to go for it. Now, along those lines, can I just quickly put up an extra page and we actually take that derivative? Maybe you guys have room in your notes right there because you haven't really written much of this yet. Maybe you don't. Try to fit it in. How would we take this derivative with respect to time? There is a lot of things. Uh-oh, I need my 1/3 in there. First of all, how would I take the derivative of v? That's the first big question. We have 1, right? And then, yeah, like dy dx, we have dv dt. Is that okay? Okay, now how are we going to take the derivative of this next side, though?
Well, isn't pi just a...
1/3 can just stay.
Isn't pi...
Is just a constant, so that can just stay.
And
So
then
what
2r.
about
2r.
Hold on. No one say bring down until we think what rule we have to stay within. Okay, do you see it? Now, for my brain, I'm just going to lump those in as constant multiples. But if your brain wants to keep the 1/3 out and the pi out, and then just don't forget to distribute, eventually you can do it that way. My brain just, I don't know, it likes it a little bit better if I lump that 1/3 in with my r squared. Do you guys see why I separated r squared and h? Aren't they both variables? And isn't there a times? So no bringing down until it's time to derive that piece, right? So second, d, because we're doing derivative of box or first prime, right? So what am I bringing down? The 2, so I'm going to go ahead and just make it 2/3 pi, because that's just a constant. And then I'm going to have r to the 1 times, what's my u prime? I have to remember my chain rule. Yeah, dr dt. This is where it gets a little weird, but you guys are used to seeing y's, taking d dx of y's and having dy dx. Now some of you just memorized it and you didn't really think about what you were doing. But that's okay, you'll memorize this as well, hopefully. Some of you guys kind of understood that when you were taking the derivative of a y with respect to x, these didn't match, therefore I needed a dy dx, whereas if you were to take the derivative of x, it'd be 1 dx dx, which just goes away. So we just leave it with the 1. That's what's kind of going on here. The r and the t doesn't match. The v and the t doesn't match. We're taking the derivative with respect to a third or another, I should say, fourth variable. So anyway, second t first, we have a little dr dt u prime plus first t second. Oh, wait a minute. What's the derivative of h? dh dt. So what's going to show up in these related rates problems are multiple, check it. How many rates do we have? 3, and are any of them the same? No. I'm not saying they can never be the same, but in this example, we have 3 completely different rates. And implicit differentiation problems. Go back and go to those notes. That was section 7.7. Sorry, I'm in algebra first, so I'm here in a second. 2.4? 2.5?
What is it?
2.5. 2.5. Look at all those implicit differentiation problems.
Okay, yeah.
Did you have multiple rates in there? Multiple of the same. Lots of dy dx's, or sometimes just one dy dx, right? If you look at any of those problems. You had lots of different rates, but they were all dy dx's. So we were all like, oh, get all the dy dx's on one side, and then move everything else over. But question, can I get everything on one side? Here. No. So let's talk about this really quickly. Okay, so for related rates, we're going to have multiple rates. And let's say multiple unique rates, meaning they're not the same. We can't just get them together. They're going to be unique rates. So really quickly, just in context of like the AP, they're going to ask us what this means. All right? I'm going to put really quickly a d box dt. Why? Because there's going to be different stuff that shows up in the top. Look at it. There was a dv dt, a dr dt, a dh dt. So you're going to see multiple rates. Or you should, if you take the derivative appropriately, implicit differentiation, remembering your chain rule. These little rates should pop up at different places. When you see them, or when the math gets them to you, or when you solve for them appropriately. What are they talking about? Well, it's talking about the rate at which box is changing. And if d box dt is greater than 0. If it's a positive rate, then I know that box is increasing. And if d box dt is less than 0, box is what? If I have a negative rate, decreasing. Now, if I were you guys and you're highlighting, especially in terms of sorry, Madison. We figured it out. Hope you're doing okay. Okay, if you're highlighting for the AP kind of person, this is a very important box. For the long answers on the AP. For the long answers on the AP. And for related rates in general. Whenever you see, well, hold on, let's practice this, okay? So, dv dt, what does it represent? The rate at which, who's in the box? which is not, oh, sometimes it's velocity, not in this context. Good, so this is dv dt is representative of the rate at which volume is changing. Good. If it's positive, volume is, and if it's negative, volume is. Good. Okay, this one, dh dt is the rate at which height is changing. Height of the water in the cone, right? If dh dt is positive, height is increasing, and if the dh dt is negative, then what is decreasing? No, the height. So rate at which this is changing is represented by d box dt, whatever's in that box, h dh dt, v dv dt, r dr dt. So if you see these words in a problem, or you see changing, or you see increasing, or decreasing, these are all pointing back to differential expressions, d box dt. Okay? So you could be going from here to here, taking this and then actually explaining what it means, or you could be reading a problem, reading these words and being like, oh, they're talking about this, or they're talking about that, etc., etc. So increasing, decreasing, changing, rate, all of these words point us to these differential expressions. Okay? But implicit differentiation, you guys see it, right? I'm taking a derivative of an entire expression as it is, right? And then, do you see chain rule needing to happen, like derivative of v is 1 dv dt? The derivative of, Mariah, you were saying bring it down. You were totally right. Bring it down, but then we also needed a dr dt before we moved on. Anyway, let's get back to the full situation over here. So, intro. And when, oh, why can't I see my page? And why is, oh, there we go. Now it's all better. Okay, in one situation, are the rates of change of each quantity the same? I know they look differently, dv dt, dr dt, dh dt, but do I just need one rate to plug and chug and be like, yay, done? Are they all the exact same? That's the question I want you to ponder as you look at this situation. Water, filling the cone, true?
Yes.
Volume is changing, height is changing, radius is changing. Are they all the same number?
No.
Question, what's happening right now? Time is going at a constant rate. Time is moving at a constant rate. But do you see what's happening? It's filling, and now, is it actually filling up slower? No. The volume of like the little water hose or the rain or the whatever is filling this up, I don't even know. Okay, then they stop filling at a certain point. But you guys saw that it slowed down, true? Okay, but let's assume that the volume coming in was at a constant rate. Why did it start slowing down? The radius was getting bigger. So didn't it take more time for the volume to raise in height? Does that make sense? You guys kind of know this situation, or you know this example. Maybe not filling up, but maybe, well, maybe filling up, but maybe it's more like draining out. You guys ever, like, I don't know, you're pouring something out of, I don't know, like a 2-liter soda or like a Martinelli sparkling cider or something like that. And it's like, oh, okay, like it's going. And what happens when it gets to that little narrow part of the bottle? It's like, zoom, and it's gone, right? Whenever you're trying to funnel something out or whenever you're trying to pour something out. Why is that true? It's because of this idea as radius increases, right? As radius increases, isn't the height going to go slower and slower and slower? But here's the weird thing. The volume in is a constant, is usually a constant. Now, could you be like putting a kink in the water hose, and could something be, yeah, you could. But generally, if you're like there with a water hose, isn't the water coming out just normal? True. Okay. So all this to say, the radius is changing. The height is changing. The volume is changing. But are they all the exact same number? No. It doesn't even make sense. Now, if I was to poke a hole in this and it was to start, or even, ooh, here's a good one. Don't you guys ever play games? And maybe we don't do the good old-fashioned, like, actually talking and hanging out with people games anymore. But, in person anyway. But, don't you ever have, like, some of those timers, right? Yeah. You're trying to, like, guess, I don't know, like, categories or something. And you're trying to, like, guess different categories, or you're trying to do this, trying to do that, trying to draw a picture with Pictionary, I don't know. But then the timer's going, and you're like, oh, I have so much time, I have so much time, I have so much time, but what happens to those? Right? It's like, and it's just, oh. And if you're on the other team, you're like, you're done, all that stuff. But anyway, it's this idea These rates are changing different to each other. Anyway, all that to say, we need to have some sort of relationship like the v equals 1/3 pi r squared h in order to talk about how all these rates relate to each other. Ooh, how all these rates, d box dt, relates as some sort of equation that kind of puts them all together so I can solve for one given another, etc. How all these rates relate to each other. Here's one more reason as to why there's absolutely no possible way that all these rates could be the same. Guys, do you see how the radius and the height are measured in meters? Right? And then the fill rate is measured in meters cubed per minute. Is it possible that one rate at meters per minute could be the exact same number as meters cubed per minute? Does that make sense? Aren't they being measured in totally two different ways? This is just a length and this is a volume. Why would the numbers be the same if their units are totally different? There's another just little silly idea. So anyway, going away from this, I just want you, and with all of these problems, to keep in mind, you know that when you're draining something out, or when you're flipping one of those little sand timers, and you're trying to think about how fast it's changing, as the radius decreases, the draining will go faster. As the radius increases, the draining will, or the filling will take longer. You know that rates change in your head, even if mathematically sometimes you're going to forget it. So let's get to an example. Here we go. And let's kind of label a few things of the math that we've already done. I want to try to make this big. Let me make it big just for a second, and then we'll come back. Because this is the exact same, slightly similar example, except in this one, you guys see the puddle of water, right? Is this one filling up or draining out? Draining. Yeah, here we go. Finding related rates. In the conical tank shown in figure 2.333, sorry, no, 2.33, whatever, that picture. The height of the water level is changing at a rate of negative 0.2 foot per minute. Ooh, that's awkward, but it's not multiple feet. Do you get it? It's foot, feet, and the radius is changing at a rate of negative 0.1 foot per minute. What is the rate of change in the volume when the radius is r equals 1 foot and the height is h equals 2 feet? Does the rate of change in the volume depend on the values r and h explained? Is this a very full-looking problem?
Yes.
Yes. But to be honest, out of all the different word problems that you might see, this one is my favorite. Not this specific, like the cone and the water tank and the water coming out, but the related rate one. Because it has such a pattern that you can follow every single time. Which is why I was able to write on the page before this little yellow box where I'm like, man, if you guys can get this down, you're going to be golden. So hold on, let's come back. Let me give you guys just a second to write down whatever you think is important. Ready, set, go. You're going to have to do this in a moment. But think. Do I really want you guys, just what my intent is, do I really want you guys writing down every single word and every single homework problem? No. I want you taking a big lump of information and summarizing it down to the key points. Oh my goodness, that's in every class you've ever taken, right? Read comprehension SAT.
The water tank with H2O is faster than
Careful, because H is going to be standing for height.
the floor.
There's a thing called shorthand. Maybe some of you guys have heard of it. Maybe some of you haven't. It's a thing back in the day before we had like dictaphones or before we had like recorders or before we had whatever. Secretaries had to take notes from their bosses very quickly. Whether guy secretaries, girl secretaries, let's not get feminism right now. But anyway, they used to have to take notes, and so whether the boss wanted to write a letter to someone, whether he was trying to give like meeting notes or something else that he needed written down, the secretary's job was to make that process simple. There's something called shorthand, where there were little symbols, there were little like ticks and notes. My mom took it in college. Other people, a lot of business majors did. Secretarial sciences people did. And there was a way of basically getting every single word down in a very, very fast fashion. Some of you are trying to do that. Okay, I'm going to take every single word and make it shorter. That's not the point of summarizing. It's not to get every single word down. It's to figure out what is the key information, right? We're not trying to do shorthand. We're not trying to just do approximations. Like, whenever I see the word the, I'm going to put like a little line to, don't do it. What's the important information that you found? Someone tell me something.
Change of rate for water is 0.8 to FT.
Good. I would go in order too to make sure you get everything. If you jump all over the place, then you're going to probably miss something, right? So, in the conical tank, can I tell it's a conical tank if I draw a cone? Okay, do I really need to write in the conical tank?
Yeah.
No. Does whatever figure it is in my book make any difference as far as me solving the problem? No. So forget that whole first line, draw a cone. The height of the water changing. Kyle, the height of the water changing, that's the one that you just pulled out, right?
Yeah.
Okay, so we're forgetting that information because whatever, draw a picture. The height of the water level changing at a rate of, okay. According to what you just wrote down, what I put in the yellow box, it's not a forever card, but it's still super important. How can I write that mathematically? So much simpler, so much faster than writing any of those words. You see it?
Yeah.
So why not just type, or write the word, not type, sorry, given, and then just say, oh, the HDT is equal to negative 0.2. Does that get that entire line?
Oh, that's intense.
Right? That entire line. Right there. No big deal.
Maybe.
So when you're putting down information for homework, do you need to write the paragraph? No.
No.
You need to pull out of the paragraph the information. See? D box dt is the rate at which height is changing. And they told us, oh, hey, that's negative 0. Oh, that means it's decreasing, right? It meaning the rate of height. Okay, what else is something else important? You have to get all the important information. Yeah, you guys are starting to do it, right? The radius is changing at a rate of, sweet. So let's go ahead and say, okay, we also know dr dt is equal to negative 0.1. I'm going to say feet per minute, just sounds better, but whatever, I understand why they put that. Okay. Now, as soon as you see a question in a math word problem, shouldn't you be like, ding, 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 I probably need to solve for it, right? So is that going to be a given, or is that going to be a find? Mm-hmm. So what do I need to find? What is the rate of change in the volume? So what am I supposed to be finding? dV dt. Now, hold on, there's this word when, right? Ooh, such that. Don't we have a way of doing such that? Okay, sweet. So let's come down here and say, okay, we want to find, right? dV dt such that r is equal to 1 and h is equal to 2. Did you put feet in feet? Of course we could.
That just made it so much more simple.
But look at it, an entire paragraph of information in 1, 2, 3 lines, and they're short, and they're sweet, and they're simple. Now, there is this whole, like, explanation part, so I'm going to be like, come back to the problem in just a second and figure out what on earth is going on here, right? But for right now, question, doesn't this actually give us an objective? Because just a second ago, we said, hey, there's this volume formula, and if you wanted to just draw an arrow to it, there's a volume formula that relates volume and radius and height of a cone. And I know that volume formula, or I should be able to find it. And just a second ago, we took ddt of the entire thing, and we got dv dt. You can just draw an arrow, it's totally fine, you can use it, is equal to, second d first, sorry, h. I'll take out the h. 2/3 pi r dr dt times h plus first d second 1/3 pi r squared dh dt. This is what we got just a second ago, right?
Yeah.
So guys, look. Isn't this something down below that could be substituted in for, right? So check it. What don't you know? Well, I don't know this. Well, good thing we have it to plug in, right? What's something else I don't know? Well, I don't know this. Well, according to my such that, we have that to plug in. That's a constant. That's a constant. H, we don't know. Oh, don't worry. I have that. Now, it's not always exactly perfectly like, hey, they're all right here. Sometimes I have to go off to the side and think about geometry or think about algebra or think about a clue and do some other plugging in. But this one's one of the most basic ones because check it. Don't I have something for everything? Right? So what am I supposed to do? Find him. Where is he? Right here. What can I do with the entire rest of the problem? Plug and check. Wait, are we even done? Yes. Really? And then you're done. So therefore, solving my related rates, I can say the rate of change of my volume is changing, or I should say the volume is changing at a rate of, well, I would plug in my R is 1, my dr dt is negative 0.1, my h is 2, plus my 1/3 pi r is 1 squared, which is just 1, and my dh dt is negative 0.2. Now, is that messy? Yes. Is this a word problem? Yes. So what are you allowed to do?
Box it in, box it in.
Except, didn't these guys have units?
Yes.
Well, no, but volume can't be measured in feet per minute. That doesn't make sense. Volume doesn't measure in feet.
Whatever.
What would happen if we did what we call dimensional analysis and if we had actually incorporated all of our, hey, that's feet per minute, and that's feet. Wait, feet, that's going to be feet. Doesn't that make sense with what we're measuring? Now, there might be some like, hey, there's feet and then there's miles. Oh no, I have to convert. Or minutes and seconds. Oh no, I have to convert. We'll have to keep an eye on the units. But guys, as long as you say, hey, that's it, and feet cubed per minute, should you probably plug and chug it to a calculator to check with the decimal in the back of the book? Yes. You should make sure you're right. But technically, in preparation for the AP, we could just box it and be like, hey, you figure it out, if it was a long answer. Now hold on, this says, does the rate of change of volume depend on the values of R and H?
No.
Question, is this a water hose with constant volume coming in, or is this how much is coming out? Forget it, look at your equation. If you plug in a different R and a different H, is it going to change what it equals? Yes. You can also think about your example about like where R is and how quickly the volume is coming out. That's mind-boggling. Guys, we have an intro to related rates. Get out of here. Chapel Day. Thanks for the extra 30 seconds. I'll see you later. Where you are like in the level of the funnel. They said where R is. If you go into physics, where you are in the radius is going to be different pressure.
Those are lovely
That's
ideas.
being put on the actual surface. So at the very end, when it goes fast, how much water? Not much. But do any? Yeah.